Swayam Prabha. Digital India. Educated India.
Welcome to 16th lecture, our video course on tribology. Today's topic is solid and semi-solid lubricants. Solid lubricants were discussed in previous lecture, but mainly on polymer based solid lubricants. Today we will be continuing with the solid lubricant as well as we will cover semi-solid lubricants. Second category in solid lubricant is the metal solids. As it was described in previous lecture, that we are emphasizing the word solid because the metal can be used as a liquid lubricant also at high temperature, but we are not mentioning about those. In solid lubricant we say that the metal solids. Basic phenomena, basic mechanism behind solid lubricant, particularly metal related, is the transfer layer. Solid lubricant deposit a transfer layer on the metals which are going to interact, and that transfer layer is a lubricant layer. Just for example, we have here the two figures, two photographs. This is a stainless steel shaft, finally finished and having very low surface roughness. A component which comes in interaction is this carbon graphite seal. As I mentioned in previous lecture, we can use solid lubricant as a bulk metal or bulk material, or we can use as a final one 15 to 20 micron thick coating. Here in this case we are using a solid lubricant as a bulk material. When this carbon graphite seal comes in a contact with the stainless steel, an operating condition in transfer layer, something like this. You can see the black marks on the stainless steel shaft. This black mark have come from the carbon graphite. I mean, a layer has been transferred to the stainless steel. Till this layer is transferred, coefficient of friction will be high. After transferring this layer, coefficient of friction reduces. Something like initially coefficient of friction may be 0.4, but after getting transferred, coefficient of friction reduces to 0.2, 1.5. So, this is what we can say the lamellar solid. These metals are generally transferred. So, that is why the layer by layer can be removed from the material, and once they get transferred on the surface, metal surface or the component surface which are interacting, then they remain there at that interface for some time before they dislodge or removed from the surface. So, we say that this lamellar solid rely on a firm transfer to achieve the low coefficient of friction. One of the common example is a molybdenum disulfide, well known solid lubricant, well known lamellar solid. We say that this material has a layered structure, and that layered structure can be described based on the molecular structure. You can see there are sulfur molecules, they are molybdenum sulfide molybdenum molecules, and these are sulfur molecules. So, bond strength between the sulfur, molybdenum and sulfur is high, while there is a layer structure. After this layer there is another layer, and these layers are connected with the sulfur molecules only, or bond between sulfur molecules. That strength of that bond, sulfur to sulfur, is relatively weaker compared to molybdenum and sulfur bond. and their strength or shear strength will be weaker in tangential direction because of that. So, they can sustain compressive load, but shear strength is very low. So, they can remove layer by layer from the bulk material. So, I say that molybdenum disulfide has a strength, it can sustain even 700 megapascal compressive strength. If it is able to sustain up to 700 megapascal compressive stress, then it is as good as a steel, but tangential strength is very low, and that is why they can be used as a solid lubricants. Because of the low tangential strength, they can be used as a low friction components. One good point is that they can sustain very high temperature. This is a major reason why in aerospace related products, molybdenum disulfide is used as a lubricant. They have very high temperature stability, or whatever the components made at a high temperature, they act as a lubricant also. So, it is not only the molybdenum disulfide acts, if it is a molybdenum oxide, that will also act as a solid lubricant. There are some weaknesses of molybdenum disulfide solid lubricant. It says that oxidation rate increases. In presence of oxygen, this oxidation happens at 350 degree centigrade, and in presence of only air, no other oxygen available other than in air, this oxidation happens at 450 degree centigrade. That is why on average we say the rapid oxidation happens over at 400 degree centigrade. But there is a contradictory point, what we say that strength is a high temperature lubrication, and here we are mentioning that 400 degree centigrade will oxidize. There is a contradiction. Generally, whenever there is oxidation temperature, we try to use lubricant below that or lower than that, but here even after getting oxidized, it makes a molybdenum oxide which acts as a solid lubricant. That is why even after oxidation, this molybdenum disulfide can be used as a lubricant. That is why we say that it is high lubricant, high temperature lubricant, and the temperature even up to 1000 degrees centigrade is not big problem for the molybdenum disulfide. However, there is a problem with the moisture. If environment has a lot of moisture, then molybdenum disulfide will not act very strongly or get attached to the surface very strongly. In that situation, it will get dislodged or removed from the surface, and that is a problem for molybdenum disulfide. Excessive humidity, we cannot use a molybdenum disulfide as a lubricant. And as a previous slide mentioned, that most of the solid lubricant, they work with a transfer layer. Most stable film thickness for the molybdenum disulfide is a 15 microns. If we deposit thickness more than 15 micron, then maybe in a few cycles or few hundred cycles, that layer will thin down to 15 micron. I mean, there is no point to deposit very thick layer of molybdenum disulfide. Doesn't really work much. However, if the thickness is lesser than 15 micron, naturally the components while operating life will be slightly lesser than what we get with the 15 micron coating. Couple of more solid lubricant. So, the carbon can act as a solid lubricant. It has a very high temperature, good properties of the high temperature, and that is why they act as a good lubricant, particularly the high sliding speed. Their temperature stability is even up to 500 to 600 degrees centigrade. However, because of the lack of the ductility, generally they are not very much recommended, but final the good form of the carbon is a graphite, which shows a lamellar structure. That lamellar structure can be utilized as a solid lubricant. That is why we can say graphite acts as a solid lubricant. It has certain strengths, certain weaknesses. The strength is it cannot sustain as high load as a molybdenum disulfide, but it can sustain moderate load. The load generally, or if we express in terms of stress, it can sustain a stress up to 275 megapascal. It shows a low coefficient of friction and it also has a high temperature stability. We say many times temperature stability can go up to 2000 degrees centigrade. They do not disintegrate, they do not change the material properties up to 2000, but there is a oxidation or there is a lack of the moisture, then properties will deteriorate. Major strength of the graphite is a moisture. In presence of moisture, they work very good lubricant, they act as very good lubricant, but if there is no moisture available, then there will be problem, coefficient of friction will increase, maybe say 3 times to 4 times. Another problem with graphite is that they act as a corrosion agent. So, that means it is not this kind of solid lubricant is not good for every solid material. Take a typical example of copper. If we use a copper with a graphite or graphite solid lubricant with a copper, copper will get corrosion because of nature of graphite. Another thing is that in the presence of a vacuum, they start outgassing, they start vaporizing, and then that is a detrimental to the solid lubricants. So, whenever there is a vacuum problem, we know very well polymers cannot be used, graphite cannot be used, we need to use molybdenum disulfide. That is why the most of the aerospace application molybdenum disulfide is used as solid lubricant. This is a typical microstructure shown of the carbon of the graphite. Says that if they are in perfect structure, they can sustain load, but if the load is increased beyond their capacity, as mentioned in the previous slide, 275 megapascal stress, then they get distorted, they get damaged. So, the beauty of the lamellar structure is removed in that situation. It will not longer be a lamellar structure, it will be distorted structure. That means, if the load is very high, coefficient of friction will increase drastically because of the distortion of their structure. This diagram shows a bond length. It says that between layer to layer is a 3.35 angstrom, which is a higher compared to within a layer, that which is around 1.42 angstrom. The longer the bond length, they can act as a layer structure, and one layer can slide on other layer. We did a good number of experiments on a carbon graphite material and figure out carbon graphite really requires moisture to act as good lubricant, but how much moisture? So, what we did, we used one rotary joint filled with the water. So, this is a rotary joint I am showing here. It has seals, is a primary seal, is a secondary seal, both are carbon graphite seals, and this material is a stainless steel. We are using a stainless steel so that the water is not going to corrode this surface. Stainless steel is resistance against the corrosion or against the rust. And there is a spring action, spring is shown with this structure, this hole, this O-shaped figures. Then when we fill it with a complete water and try to find out the coefficient of friction between stainless steel and carbon graphite, it reaches even to 0.4, 0.5. But if we reduce this and just allow some moisture to be made, water here, you can see here the water level is almost negligible, only a small tip of a stainless steel is dipped in water. What will happen in this situation, level of availability of moisture between the interface carbon graphite and stainless interface is reasonably low, and we find the coefficient of friction is very low, in this case is equal to 0.15. If we do not use a moisture at all and run this structure or this unit at 100 degrees centigrade, we find high coefficient of friction almost 0.25. So, moisture is necessary for carbon graphite, but too much moisture is more problematic. At the very high level of moisture, they get more and more wear rate, because layer formation or transfer of the layer on the stainless steel is very high, and thicker the layer, brittle will be the structure, it will get damaged immediately, will get in wear debris immediately. So, first is that rate of the transformation is high, and the deformation or dislodging of that wear transfer layer is high, and because of that there is a high wear rate, as well as coefficient of friction is also reasonably high in this situation overall. So, we can say that maximum wear occurs under complete water environment, when water environment too much water is present. That means, we should not use too much water, and minimum wear occurs under the vapor lubrication, when there is just sufficient moisture available, which makes a water vapor, and then they act as a gaseous lubricant. So, that is a situation with the carbon graphite. Now, if we try to summarize a carbon graphite or graphite structure, what we say? They have a high thermal stability even up to 2000 degrees centigrade, but there is a limitation. First thing is the moisture will not remain there, water vapor will not remain there at a high temperature, and because of that coefficient of friction will increase, wear rate will increase because of that. So, there is a practical difficulty, practical limitation on carbon graphite. There is another good point is that this low coefficient of friction basically depends on the moisture, and some experiments done in the lab indicates that, and when there was analysis of a component failed during the World War II, it was indicated there clearly at a high altitude, generally electric motor brushes, carbon graphite is used to make electric brushes, they failed, and after doing a research, doing analysis, it was figured out that adsorbed layer of water vapor, which was supposed to lubricate effectively, was lost from the surface. That is why there was a high coefficient of friction and high wear rate during World War II in equipments which were used. As I mentioned, it corrodes the surface, as it has a potential of plus 0.25 volts. Whenever materials have this kind of potential, they will corrode the few material surfaces, and that is why I say that it will cause galvanic corrosion of copper alloy and to some extent stainless steel, but in presence of say salt which is available, or some sort of acid environment. Last solid lubricant what we are discussing in the present lecture is based on ceramics. So, the ceramic materials, good point of the ceramic material is that they have a less chemical reactivity, and they have a high temperature stability. So, that is why this kind of lubricant can be utilized for the high temperature applications, but they have a brittle structure. That is why we say that the coating thickness should not be more than 0.5 mm. More than this thickness, then there will be a fragmentation, fracture of that layer because of the brittle structure, and we should not use that. Now, to deposit this kind of a coating, we have special techniques available. First and cheapest technique is the plasma spring. Detonation gun is another one, and finally is the electrolytic deposition. It is more like a dipping coating. Coating is deposited by dipping that substance, making the electrode connections. When coming to the detonation gun, we use high velocity to impart kinetic energy to the surface and give some sort of penetration or diffusion mechanism, so that coating remains in contact with the material which require coating. Plasma spring is generally high temperature coating. it is a easier one to deposit the high temperature and then cure it, maybe at air environment curing or good regulated temperature environment. The only problem with plasma spring is a dimensionality. There is a possibility of change in dimension. So, we need to, after doing this kind of coating, we need to do a super finishing operation on those components. And these coatings are now well known for as a wear resistance compared to the friction reduction, compared to the lubrication. Reduction in friction occurs because of the low chemical reactivity or low adhesion, but abrasion will be rare as they have a very high hardness. That is why they are known as a wear resistant coating compared to friction reduction coatings. Now, we will start with semi-solid lubricant, and a typical example is a grease. Number of other materials which act as a semi-solid or the gels, they can be used as a lubricant, but grease is a more popular, it has a wide application compared to any other semi-solid. So, that is why we are discussing about greases. Now, in grease, if you see the structure, it looks like a jungle. You can see this structure. Yeah, I can assume there are number of wooden pieces. These are the actually fibers. They make a structure such a manner liquid cannot escape easily. So, this structure need to be filled with the lubricants. That is why I say that it consists of the base oil as well as additives and thickness, and this is what we are showing here, the other thickness. This thickness make structure in a such a manner that liquid cannot easily escape from that integrated part, or maybe can assume that it acts as a sponge, and a sponge has a capability to retain the lubricant within it. It can be, in layman language, treated as like a sponge, and this thickener fibers are roughly 5 to 20%. Oil which is basically used to lubricate the surface contains from 75 to 95%. In addition, we may require additives to reduce oxidation at a high temperature, to sustain extreme pressure, high loads. If there is a water environment, to avoid corrosion of the components, or maybe some water repellent. So, these can be acted as additives. Coming to the base oil, which is a main constituent. So, the base oil can be mineral oil, can be synthetic oil. More popularly in this is the synthetic oils are used because of we can design these oils and with the proper properties. Coming to the mineral oil, sometimes we say the low viscosity oil and high viscosity oils. When talking the low viscosity, generally they use for the low temperature, because with increase in a temperature we know the viscosity will decrease. That is why the high temperature we use high viscosity oils, because as the temperature increases they will turn out to be a low viscosity oil at high temperature. But when we measure the viscosity and we coat the viscosity, generally 40 degrees centigrade, and classification basically is of 140 degrees centigrade. 40 degrees centigrade low viscosity has a low overall value, maybe say 30 to 50 centistroke. Coming to high viscosity, even to the high viscosity maybe say 200 centistroke, when it is a resist to the 100 degree 150 degree centigrade where the temperature this kind of oil should be utilized, the viscosity will turn out to be again the low viscosity. So, effectively what we are talking about the high viscosity oil at the low temperature, but they will turn out to be low viscosity at the high temperature. And this kind of viscosity, low viscosity oil can be utilized at the low loads and high speed application. Particularly high speed application is emphasized over here, because the high speed application there will be more and more shearing. If there is a more shearing, more friction means heat generation will be more, temperature will be high, and then again the viscosity will turn out to be low if we use a very high viscosity. So, there will not be much effect of using high viscosity except the losing energy. While coming to the high viscosity, one application I mentioned is the high temperature, other application is the high load. If the load is very high and we do not want the oil to be squeezed out from the interface, then we should use a high viscosity oil. And high load with a low speed operation, it should not be the high load and high speed operation, then you need to use a good lubricant. Ordinary mineral oil or ordinary high viscous mineral oil cannot be used for this kind of applications. As I mentioned, the last is thickness which act as a fiber and they make a structure, they are main components. And that is why I say when grease life is over, grease need to be discarded. Reason is oil is getting separated from thickness, or what we say grease is bleeding or grease bleeded. That is why we need to replace this grease with a new grease, which is a new and oil is retained within fibers. Coming to the thickness, we say thickness can be defined in number of categories, which we call as the soap based thickness, the process in which the thickness are made to convert in grease or to find the grease. They are generally simple soap base, complex soap base, and there are other kind of non soap base also, where the clay is used to make grease. However, the soap based greases are more popular or most commonly used unless we require a high temperature application or severe load applications. Again, in simple soap we use only one acid with the metals, while in complex soap we use two acids. When there is a two acid, there will be hybrid structure. Wherever there is a hybrid structure, there is a more possibility to sustain high temperature. That is why the complex greases can be used for the high temperature applications, while simple soaps can be used for relatively low temperature applications. One of the most commonly used simple soap grease is a calcium based soap grease. It is most commonly used and many times it is called all purpose greases because it has temperature sustainability up to 65 degrees centigrade, and operating temperature is not going beyond 65 degrees centigrade. Calcium grease will work very nicely, generally used for the low speed applications. However, lithium grease is now gaining more popularity because of the structure, because of its high temperature stability. Even in lithium can be used as a complex greases. So, lithium grease is a more known, more popular from temperature stability point of view or operating temperature point of view. As I mentioned, there are non-soap greases also. They are basically clay based and they are mixed also with the solid lubricant. You can see here the PTFE based grease can PTFE act as a solid lubricant in that. There are some synthetic greases, polyurea, ceramic paste, alumina, silica gel. There are sometimes we call classify greases based on their additives. Like one of the popular name is a moly greases, as based on the molybdenum disulfide grease, graphite greases. The solid lubricant is used to reduce the coefficient of friction, to transfer layer, and basically a grease is used as a carrier media in that, as well as sealing medium. EP greases with the EP additives are mixed with the grease. And what we say then in the layman language, grease is more like a black or yellow sticky mass. That means have always some sort of fatty acids which will stick to the surface. Is a sticky mass most commonly used for the bearings. Talk about any rolling element bearing, by and large greases are used as a factory lubricant. So, that's why I say that in layman language we can say there is some thick mass used for the lubricating the bearings. Now, this slide shows a comparative chart, so that we have clear idea which grease should be selected. I am just giving this example because we made one test setup for one textile machine, and we were supposed to operate bearings at 2500 degrees centigrade. Assembly was made, and before supplying that assembly or test setup to us, a vendor started working, wanted to check with the motor which was used is sufficient to supply power or not. That is why he used a calcium based grease. Of course, without knowing that that is a calcium based grease, he used ordinary grease which are available in the market, and he used that grease. And surprisingly, within a few minutes, whole grease turned out to be black powder, and whole assembly was stopped. Motor was not able to supply the power. That is why he called me and he says that, sir, what should I do? I did this, and before supplying to you, I checked in my premises. We simply say that you just change bearing, because once grease failed in bearing, we need to replace the bearing. Replace bearing and use a lithium based grease, which was supplied to him, and interestingly the test setup after that never failed. It worked very well. It is just a high temperature which makes calcium grease as ineffective grease, and lithium, which can sustain high temperature, can be used as a good grease for that application. So, this chart shows the comparisons. We say the dropping points. First, the dropping point is the maximum temperature at which a grease can be utilized. After that, the bleeding will be very high. Almost all complete oil will be removed from the surface or within a structure of grease. So, when we use a calcium, by no way we should use more than 80 degrees centigrade, and what we call as a maximum operating temperature, keeping a factor of safety into account, we say that it should not be utilized more than 65 degrees centigrade at all, while lithium based grease can be used for the 125 degrees centigrade. So, there is a huge difference of 60 degrees centigrades. Generally, operating temperature is 40 degrees centigrade. When we operate it, friction will be there, heat generation will be there, and that is causing an increase in temperature. So, 55 to 60 degrees centigrade temperature can be assumed for the high speed applications. Now, there is another kind of the sodium based grease, which has also operating temperature 125 degrees centigrade, but which is the problem is that it cannot be used for the low temperature applications. They start freezing, and another thing is that they are very reactive with the water environment. They should not be used with the water environment. They start making components, and then they will turn out to be ineffective solid ineffective greases, ineffective semi solid lubricants. When coming to the complex greases where the two acids are used, we can see that significant improvement in the calcium based grease. You can see calcium based here, it was only 80 degrees centigrade. When we use with the two acids, then it can sustain maximum temperature, or so the bleeding starts at 260 degrees centigrade. Of course, maximum operating temperature is still restricted to 150 degrees centigrade, but still that is temperature is far above than the 65 degrees centigrade temperature. Even lithium based grease is also 125. So, what we can say, the complex greases when it is made, it gives a maximum advantage to the calcium based greases. It does not give that much advantage to the lithium based grease. You can see the lithium based grease with a complex structure, the two acids which require the more manufacturing steps, is 160 degrees centigrade, while here it is 125 degrees centigrade. So, improvement in this operating temperature is not very high, right. And of course, with all other parameters, they are working fine and they show the good resistance, good performance. Coming to the clay based, so the polyurea based, we can see that is all as good as complex greases. More or less complex greases have 260 degrees centigrade as a dropping point, while polyurea is 250, and operating temperatures are also more or less same. You say 150, 150, 150, 160, 150. So, by and large we can say the maximum temperature, operating temperature for the grease is 150 degrees centigrade. We should not use more than that. Whenever the temperature is more than 150 degrees centigrade, we should switch over to some lubricating oil which have heat carrying capacity or heat dissipation is much faster compared to greases. And another important thing is that if whenever we choose, first if there is a water environment and the operating temperature is 50 to 60 degrees centigrade, we should choose the calcium because it is economic, is a least costly, or it is not as expensive as other greases. And we have a doubt about the operating temperature, we are not sure, then we should choose the lithium based grease, because the lithium based grease is the costlier, but it gives a good performance from every angle, maximum temperature, low temperature, water resistance, oxidation resistance, that way. When coming to the complex greases, we can find out all good performance from aluminum based greases or lithium based greases, but lithium complex will be costlier compared to the simple lithium greases. So, unless it is really required, we should not use. This is this slide shows what is the importance of mineral oils or silicone oils or synthetic oils. What we talked in previous slide about the thickness, using different thickness how the performance will change. But when we talk about the thickness and select this thickness, particularly with the lithium base or aluminum based or polyurea base, we need to think about what should be the carrier fluid or what will be the base fluid which is used with grease. Here the if I am assuming that we are choosing a lithium based grease for our applications. So, there are three categories, is a mineral oil, is a esters and silicones. Silicone is one of the costlier. That is why we say that overall lithium based grease based on the silicone oil will be costly. Coming to the mineral oil is cheaper than the synthetic oils, then the cost will be medium. Of course, so we are talking the medium because we are comparing with the calcium. The calcium has the lowest cost. Now, what we get from this, when we do good processing, then temperature can be increased, and in this case we are talking about the lithium with plus mineral oil plus some additive package including the heat resistant package. We find that maximum temperature it can sustain up to 150 degrees centigrade, which was with in previous slide we talk about the complex lithium based grease. However, the minimum temperature you can see that it cannot be operated lesser than minus 40 degrees centigrade. If we want better performance at the low temperature, we can switch over to the different lubricating oil, different base oil. What we are doing here, mineral oil is been replaced with the esters, and that the operating temperature, low operating temperature is minus 75 degrees centigrade. So, almost 35 degrees centigrade difference is coming just by changing the lubricating oil. However, the cost is increasing and it is getting penalty at the high temperature. While we want a overall very good performance, a low temperature good performance, or a high temperature good performance, then we should choose lithium based grease based on or with a silicone oil, which is also a popular grease, but high cost grease. Now, this slide shows some advantages of the grease compared to solid lubricants as well as liquid lubricants. Compared to solid lubricant, we say that one of the major advantage is it remains in contact with the surface that can be replaced easily, and a liquid lubricant we require frequent supply of the lubricant. That is why we say that is a less frequent application is needed when we are comparing with a liquid lubricant. Comparing with a liquid lubricant, we say that it is seals effectively. That means from environment contamination will not come easily, and it will not be requiring very a tight seal, and ordinary seal can be utilized effectively with greases. Good point about this greases is that as they are not able to they are not allowing the contaminants to come into contact with the metal surface, they can be water resistant also. And the important thing is that even the worn out parts can be used effectively with the greases. It reduces the vibration, it reduces the impact loading, it can sustain the shock loading. So, what we say that is gives a maximum comfort. That is why with most of the rolling element bearings, even they develop small pits at the initial surface, initially they can be used effectively with greases that will give the good results. This sketch shows I am just assuming there is one initially the solid surface, and when solid surface develop pits, maybe due to fatigue loading, then if there are pits, naturally there will be a vibration. If any rolling element passes on the surface, it will come with some sort of contact and non-contact, contact and non-contact. That means the stiffness will be very high, low. When metal to metal contact is there, there will be high stiffness. When there is no metal to metal contact, stiffness will come down. So, there is a continuous variation in stiffness that will induce a vibration phenomenon. And if we are using the greases, what will happen in the situation? Grease will fill these pits. When the pits are filled, then vibration level will be reduced. They will act as a damper. They will act as a reduction in a noise agent. They will reduce the noise in overall. So, grease is effective to reduce the noise, to reduce the vibration, to reduce the impact loading on the surface. They have capabilities to absorb the energy by deflecting from the surface and regaining the shape. There are a number of disadvantages of the greases. What we say that it has a low fluidity. So, heat dissipation is a problem because they have a low conductivity also. We mentioned about the advantages that grease retains or avoids the particles to come into contact, or avoids contamination to come into contact with the solid surface. It prevents the contamination to come into contact, but problem is that once the contamination start coming, one way or another they reach to the surface, then grease will try to retain those contamination with the surface. That means, it has advantages is that they are able to avoid prevent the contaminant to come into contact, but once they come into contact, then there is a problem. We need to replace the grease, there is no other way. We cannot do any filtration of that kind of grease. So, it has advantage as well as disadvantage. Generally show high coefficient of friction compared to liquid lubricant, but low coefficient of friction compared to solid lubricants. Now, as I mentioned, it shows a high coefficient of friction, but a few experiments indicate not necessary high coefficient of friction is done or is achieved by the using grease as a lubricant. We can many times mention that they show low coefficient of friction, typically if the operating speed is low. So, this chart indicates the friction torque generally related with coefficient of friction, and this axis shows a speed or sliding speed in meters per second. You can say that A chart, which has used, we are using only liquid lubricant, is showing very high friction because there is no hydrodynamic action, and when the applied load is high, this lubricant is simply squeezing out without effectively reducing the coefficient of friction. Now, if we increase the grease, so B is aluminum, C calcium base, sodium base, and then finally comes the lithium base. With the change in the grease, we are seeing the different behavior. Their load carrying capacities are different, and that also indicates the lithium based grease is showing very high load carrying capabilities, as well as more or less same constant friction force. When I compare E versus A, we can say E is showing a much lesser friction compared to A. A is a liquid lubricant. So, studying this one, the high coefficient of friction from the grease may not be 100% correct. It is for the high speed application. For low speed application, this sentence is not correct. For low speed application and a high load, we can say that lithium based grease can show better performance compared to liquid lubricants. We have some methods to characterize or characterize a grease, what we call as a cone based method. You can see this cone over here, and this black surface is a grease surface. We point on the surface, or this cone point comes in the contact with the grease surface, and we allow 5 seconds. It is a free fall of this cone, of course the guided one, free fall particularly in the vertical direction of this cone. Within 5 seconds, whatever the depth of the cone is achieved within a grease, that informs us what is whether the grease is consistent or not, or how much plastic deformation can this sustain, this grease can sustain. That is why there are different numbers given to that, and of course, this grading is done by NLGI, what we call as one of the American institute, National Lubrication Grease Institute, National Lubricating Grease Institute. That is why the NLGI word is used. We characterize grease with NLGI grades. We say the 000, they act like a liquid lubricant. Okay. And what we are talking about, this penetration or this kind of experiment is done at a 25 degree centigrade, and this number signifies as 1/10 of mm. Within 5 seconds, if you are using this grease, within 5 seconds, this cone will penetrate up to 44.5 mm. The maximum is a 47.5 mm. The cone will fall within a grease up to this level. Now, this sketch is clearly indicating how do we measure it. There is a dial gauge. This is the initial position of the cone, and we are allowing for the 5 seconds to fall in grease. And of course, we are able to see the grease is displaced from this place to this place. That is why we are able to get this kind of shape. As the depth of penetration reduces, we call consistency of the grease is increasing, or we can say NLGI 6 grade grease is solid grease, while NLGI 000 grade grease is a liquid grease. Flowability of the NLGI 000 grease will be very high compared to NLGI 6 grease. By and large, we use a second or third NLGI greases for the rolling element bearings or common applications. To model this kind of grease, we use some sort of fluid law, maybe Newtonian law, maybe shear thinning law, shear thickening law, or Bingham law. But we know very well that grease act as a pseudoplastic. They show the shear thinning behavior, but they also show some resistance in the initially, or in other word, we say that grease gives some resistance initially, it does not move, shear rate will not be developed at all. That means, initially shear stress will be there, and after that it can show some sort of Newtonian fluid or some non-Newtonian fluid or shear thinning behavior that we can use, we can add this tau 0 in this component. That is why we say that for grease we can find out tau I, interface shear strength as a tau p, that is initial shear stress required to flow the lubricant, flow the grease. This is a viscosity. This is a viscosity over here, and this is the velocity gradient. This is another constant, which is that n is a lesser than 1 is a shear thinning, n is greater than 1 is a shear thickening. Now, what if say that in grease there will be a tau p value, there will be eta b value, there will be n value. So, there will be 3 constants. We need to find out to characterize a grease. Effectively, we need to find out 3 parameters tau p, n b and n. That is why they say that initially to define tau p we required some initially shear force. So, the viscosity of grease drops and approaches to the flowability of a liquid. To give more emphasis on grease characterization, I can take the same example which we took in the previous lecture when we defined the viscosity. There is always a one moving surface, a stationary surface, and grease also shows a similar kind of layer structure, can be removed layer by layer. Now, to find out initially tau 0, because we mentioned about relation tau p, to find out the initially tau p, we need to experiment this in a rheometer. What is a rheometer? We will describe later, but in a rheometer at a 3 rpm, we operate that rheometer at a 3 rpm with a standard size of a rotor, and whatever the resistance comes, whatever the yield strength comes, that will turn out to be tau p. To find out the 2 remaining constant eta b and n, we can operate 300 rpm or 600 rpm, or one reading at 300 rpm or the other reading at 600 rpm, and find out what is the resistance, what is the shear, what is the yield stress. Once we know the yield stress or the 2 other readings, and we can substitute tau p, which we determine at the 3 rpm, and velocity gradient, and obtain results. Based on that, we can find out what will be eta b and what will be the n. So, overall grease can be characterized by operating grease in a rheometer at 3 rpm and 300 rpm, 600 rpm. Our option is with us. We can operate both, we can take 2 different readings at the 300 rpm, and if there is some change comes, or we can take 2 separate reading 300 rpm as well as 600 rpm. I believe that operating at 3 rpm gives a tau p, operating at 300 rpm may give one constant, and operating at 600 rpm may give another constant. So, we require 3 conditions. Now, as I mentioned, the greases can be classified based on also on additives which we mix in grease, and one of the common additives is extreme pressure additive. The similar kind of additives also are used in a liquid lubricant. When we discuss with the liquid lubricant additives, when this kind of a topic will be same, and that is why I am describing only in one topic, that is extreme pressure additives for the grease. They remain same for the liquid also. You can see how they act. They are basically boundary agents. They chemically act with the surface, they corrode the surface, make a very thin layer on the surface. That corrosion is done purposefully, that is why we call that as a sacrificial layer. The sacrificial layer is made immediately, and to avoid future corrosion or future deterioration of that surface. So, they act as a wear resistant layer. So, I say that chemically this kind of additives, they chemically react with the sliding metal surface to form films which are insoluble. Mind it, these additives are soluble in lubricant, but they make coating on the metal surface which is insoluble. That is a very good action of the extreme pressure additives. So, I say that these additives are soluble, they are soluble compound of the sulfur, chloride or with a chlorine and phosphorus. And the most commonly used additives based on the metal and chlorine, phosphorus and sulfur are TCP and dibenzyl disulfide, and this is most commonly used in engine oil, what we call as ZDDP. So, zinc dialkyl thiophosphate. I mean, it has a phosphate, it has a zinc also. Zinc is one of the very good anti-wear additive metal, right. The chemical structure is also shown over here. They have a bond over here which can act with the surface and make complete this additives attached to the surface also, but there will be with the chemical action, there will not be only the physical action. Boundary additives generally use a polar end to get attracted to the surface and make a bond, while in this case they have bonds which play with the metal surface, and then this bond makes chemical or react with the chemically with the metal surface. There are some friction modifiers which are used with greases, and we are mentioning again this topic in greases, reason being they are same lubricants, the same lubricant additive which will be discussed again in should be discussed again in liquid lubricant, but I want to just restrict on only in one of this topic, either grease or liquid. So, I am just using 2 additives in grease and one few more in liquid lubricant. Now, when we use the friction modifiers, we say that they increase the film thickness or they increase the film strength to avoid surface to surface contact. Major purpose of using this kind of modifier is to increase the film strength, so that that film or that coating is able to sustain more load, and possibly then they should provide some cushioning effect also, so that the 2 surfaces remain without much contact. Now, by and large friction modifier we know as they are used as a boundary additives. They are solid lubricant. You can see that these all are solid lubricant. Moly grease based on the molybdenum disulfide, Teflon grease based on the PTFE, graphite grease is again a solid grease. So, these are used with this kind of greases, and one of the experimental leading which we have is based does indicate what is the effectiveness of a grease when we mix with graphite. So, when the graphite is not mixed at all, the well load limit is 160 kilogram, and where is scars which we do experiments with experiment on pin on disc, we find this kind of scars, that is a 0.6 mm is one. When percentage of the carbon this graphite is increasing, we are able to see that it reaches to a 1 mature stage 225 kilogram, which is a significantly higher compared to 160, and scar is also coming down. So, this is the beauty of graphite. With this I am trying to close this lecture. We will continue on the lubricant in our next lecture. Thank you. Thanks for your attention.